picture this. It's 1950, and a group of physicists are walking to lunch at the Los Alamos National Laboratory. They're chatting about a recent string of UFO sightings splashed across the newspapers. Flying saucers, strange lights, mysterious visitors from beyond. By the time they sit down at the cafeteria, the conversation has wandered, the way physicists' conversations do, into something far stranger. And then, out of nowhere, one of them leans forward, looks around the table, and asks a question that has haunted science ever since. Where is everybody? The man asking was Enrico Fermi. And the silence that followed his question is, in a very real sense, still ringing through the universe today. Because if you stop and actually think about it, the night sky is the most suspicious crime scene in human history. Hundreds of billions of stars in our galaxy alone, trillions of galaxies beyond it, billions of years for civilizations to rise, evolve, and spread. And yet, when we look up, we see nothing, no signals, no probes, no ships hovering above the White House lawn, nothing but the indifferent shimmer of distant suns. Now, Richard Feynman never wrote a famous paper titled, "Why No Alien Spaceship Has Arrived," but scattered through his lectures, his interviews, his playful, almost mischievous explanations of how the universe really works, you can assemble something extraordinary. A Feynman-style answer to the greatest absence in science. And the answer he would give, I think, is not the one you're expecting. Because most people assume the reason aliens haven't arrived is biological. Maybe life is rare. Maybe intelligence is rarer still. Maybe civilizations destroy themselves before they reach the stars. Those are fine guesses. But Feynman, ever the physicist, would gently shake his head and say, "No, no, no, you're skipping the hard part. The hard part isn't whether they exist. The hard part is the universe itself. The hard part is physics. And physics, it turns out, is a much crueler bouncer than biology will ever be." Let's start with a thought experiment Feynman loved. Imagine you're standing on a beach, and you want to send a message in a bottle to someone on another beach. If that other beach is across the bay, easy. Toss it in. The tide carries it, done. If it's across the ocean, harder, but doable. Now imagine that other beach is on a different planet, in a different solar system, separated from you not by water, but by light years of empty vacuum, and not just 1 or 2 light years. The nearest star to our sun, Proxima Centauri, is about 4.24 light years away. That means light itself, the fastest thing in the universe, takes more than 4 years to make the trip. And light, as Feynman would remind you with that Brooklyn Queens grin of his, is not a suggestion. It's the law. Nothing with mass can travel at the speed of light. Not a rocket, not a probe, not a flying saucer. Not even a particularly ambitious photon torpedo. Because as you push something with mass faster and faster, something very strange happens. Its energy doesn't just go up linearly, it goes up exponentially. And by the time you're approaching the speed of light, the energy required to push it even a tiny bit faster becomes, quite literally, infinite. This is one of the most underappreciated facts in all of science. The speed of light isn't a technological barrier, the way the sound barrier was. It's not something a clever engineer can crack with a better engine. It's woven into the geometry of space-time itself. Asking why we can't travel faster than light is like asking why a triangle can't have 4 sides. The question doesn't even mean anything inside the rules of the game. Now, an optimist would say, fine, we'll just travel at, say, 10% the speed of light. That's still fast. That's 30,000 kilometers per second. To put that in perspective, our fastest spacecraft, the Parker Solar Probe, hits about 200 kilometers per second at its peak. So 10% of light speed is roughly 150 times faster than the fastest thing humans have ever built. And even at that absurd velocity, a trip to Proxima Centauri would take 42 years, one way. No sightseeing, no stops for fuel, just 4 decades of cold, dark, radiation-soaked vacuum. And here's where Feynman's mind would start to twitch with delight, because the energy problem is even worse than it looks. To accelerate a spacecraft the size of, say, a school bus to 10% the speed of light, the kinetic energy required is roughly equivalent to the entire annual energy consumption of the United States, for one ship, to one star. And then you have to slow it down at the other end, which doubles the energy budget. And if you want to come home and tell everyone what you saw, you double it again. We're talking about the energy output of a civilization just to send a single small probe to the nearest neighboring star and back. So when people say, surely an advanced civilization could overcome these obstacles, Feynman would push back hard. Advanced doesn't mean magical. Even a civilization a million years ahead of us still has to obey the same laws of physics. They still need energy. They still need fuel. They still have to deal with the fact that hitting a grain of sand at relativistic speeds releases the energy of a small nuclear bomb. Imagine being inside a ship traveling at a tenth of light speed, and the universe is throwing tiny invisible hand grenades at your hull every few seconds. Suddenly, interstellar travel starts to sound less like adventure and more like a slow, expensive, almost suicidal hobby. But let's play the optimist again. Let's say a civilization solves the energy problem. Let's say they crack fusion, antimatter, even something more exotic that we can't imagine. There's still a deeper problem, and this is where Feynman would lean in and start drawing on a napkin. The problem isn't just the distance. The problem is the time. Even at light speed, our galaxy is 100,000 light years across. So if a civilization on the far side of the Milky Way wanted to say hello, the message would take 100,000 years to arrive. And by the time we replied, another 100,000 years would pass. 200,000 years for a single exchange of pleasantries. Human civilization, the entire span from cave paintings to smartphones, is only about 10,000 years old. We are an evolutionary blink. Our radio signals have only been leaking into space for about 100 years. That's a bubble of detectable noise about 100 light years in radius, around a galaxy that's 100,000 light years wide. Picture that for a moment. Our entire technological footprint, every episode of every television show, every radar ping, every cell phone signal, occupies a sphere that is 1/10,000th the diameter of the galaxy. That's like trying to find a specific firefly that blinked once 2 minutes ago in a forest the size of North America, and you're searching from the moon. Feynman had a beautiful way of describing scale. He once said that the difference between a million and a billion isn't just 3 zeros. A million seconds is about 11 days. A billion seconds is almost 32 years. The numbers we use casually in astronomy hide brutal, almost unimaginable gulfs of time and space, and those gulfs are the real reason why no alien spaceship has arrived. Not because aliens don't exist, not because they don't want to come, but because the universe is built, at its most fundamental level, to keep things apart. There's a wonderful irony here. The same laws of physics that allow stars to form, planets to coalesce, and life to flourish also conspire to isolate every cradle of life from every other. The speed of light, which makes causality possible and gives us a coherent universe, is also the prison wall around every civilization. Feynman would have appreciated this paradox. He loved when nature played both sides of a question. He once said that the most exciting phrase in science isn't "Eureka," but that's funny, and the silence of the stars is one of the funniest things in the universe if your sense of humor leans cosmic. But let's push deeper, because Feynman would not let us off the hook with just distance and speed. There's a subtler argument hiding here, and it has to do with energy and entropy. To run a civilization, any civilization, you need a constant flow of low entropy energy. Stars provide this in the form of sunlight, but starlight is concentrated near stars and fades rapidly with distance. The space between stars is, by cosmic standards, freezing cold and energetically barren. Imagine trying to drive a car across a continent where the gas stations are spaced not every 50 miles, but every 4 light years. And every gas station is a star, which means you have to dive into a furnace to refuel. That's the energy landscape of the galaxy. It's not a friendly road trip. It's a desert with occasional infernos. Now Feynman, in his quantum electrodynamics work, spent decades thinking about how energy moves, how particles interact, how information propagates. He knew, perhaps better than anyone, that the universe is not a free buffet. Every interaction costs something. Every signal degrades. Every ship leaks heat. And in a universe governed by the second law of thermodynamics, every journey, no matter how advanced the traveler, is a slow battle against decay. There's a reason your phone battery dies. There's a reason stars eventually burn out. There's a reason, ultimately, why interstellar travel is not just hard, but in some sense, fighting the deepest current in nature. And then there's a question Feynman might pose with a sly smile. Why do we assume aliens would even want to come here? This is one of the most underrated points in the entire Fermi Paradox. Humans, being humans, project our own restless curiosity onto every imagined civilization. We assume that intelligent life inevitably wants to explore, conquer, communicate, expand. But that's a very specific cultural assumption baked into a very specific evolutionary history. Maybe most intelligent species turn inward. Maybe they build simulations, virtual realities, so rich and rewarding that the cold, expensive, dangerous physical universe simply loses its appeal. Why cross 1,000 light years of vacuum when you can build a paradise inside a computer the size of a refrigerator? Feynman, who famously said, "There's plenty of room at the bottom," understood the seductive power of the small. The future, he suspected, might lie not outward but inward. Not in bigger ships but in smaller, denser, more elegant manipulations of matter. And if that's true for them as well, then the great silence isn't a tragedy. It's a choice. It's a universe full of civilizations who looked at the math, did the energy calculations, glanced up at the stars, and decided to stay home. There's another piece of this puzzle that Feynman would have loved, and it comes from his approach to probability. He often warns students against being fooled by intuition when dealing with very large or very small numbers. The universe is old, yes, about 13.8 billion years, but intelligent technological civilizations might be vanishingly rare events scattered across that timeline. Imagine a vast dark theater, and every now and then, somewhere in the audience, someone briefly lights a match. The match flares for a moment and then goes out. Now imagine you're trying to spot another match lighter, but you can only see the light for matches that were lit in just the right place, at just the right time, with the light reaching you exactly now. Most matches lit 1 million years ago in distant galaxies. Their light has long passed us. Most matches not yet lit we'll never live to see. The window of mutual visibility between civilizations might be absurdly narrow. We could be surrounded by past and future neighbors, all of them invisible to us, separated not just by space but by time. The universe isn't empty, it's asynchronous. And asynchronicity in the universe with a finite speed of information is functionally identical to loneliness. Feynman had a story he liked to tell about looking at a flower. A friend once accused him of ruining the beauty of a flower by reducing it to science, and Feynman, in his unmistakable voice, replied that science doesn't subtract from beauty, it adds to it. You can appreciate the flower as a flower, but you can also appreciate the cellular machinery, the evolutionary history, the physics of pigments and pollination. Each layer makes the flower more wondrous, not less. The same is true of the night sky. You can look up and feel awe at the stars, but when you understand the actual physics, the speed of light prison, the energy barriers, the asynchronous lifetimes of civilizations, the awe deepens, because you realize that every photon hitting your retina from a distant star is a tiny ancient messenger. It left its source years, centuries, sometimes millions of years ago. It carries information about a place that may no longer exist, in a form so faint we can barely detect it. The universe is whispering to us. It's just whispering very, very quietly, in a language written in light and gravity, across distances that swallow voices whole. Now let's bring it back down to earth. Why does any of this matter? Why should you, sitting wherever you are, care about whether aliens are coming? Because the same physics that keeps them away shapes everything in your daily life. Your GPS works because we understand relativity. The satellites overhead experience time slightly differently than you do, and if we didn't correct for it, your map would drift by kilometers every day. Your microwave oven, your cell phone, your computer, every modern convenience runs on the same quantum and electromagnetic laws that govern the silence between the stars. Understanding why no alien ship has arrived isn't a parlor game. It's a window into the deepest workings of reality, and it's also, in a strange way, a mirror. When we ask where the aliens are, we're really asking what kind of universe we live in. Is it a universe designed for connection or one designed for isolation? Is intelligence a brief flicker or a sustainable flame? Are we exceptional or simply early, or simply late, or simply unlucky? Feynman would not pretend to know the answer. He was famously suspicious of grand pronouncements, but he would insist that the question itself, asked properly, is more valuable than any answer. The honest physicist's position is humility in the face of scale. There's a final twist worth considering, and it's one of Feynman's favorite kinds of twist, where the answer hides in plain sight. We've been talking about why aliens haven't arrived, but maybe the framing is wrong. Maybe arrival is the wrong metric. Across the vast distances of space, the cheapest, most efficient way to make contact isn't with ships at all. It's with information, light, radio waves, lasers, patterns of photons that can cross light years for the cost of a flashlight. So when we ask why hasn't anyone arrived, we may be asking the wrong question, the way someone in the 19th century might have asked, why hasn't anyone sailed a galleon from Europe to my front porch, when in fact a letter, a telegraph, a phone call could reach them far more easily? The real question, the question SETI researchers have been asking for 60 years, is not why no ship has come, but why we hear no signal. And here, too, Feynman's physics offers humbling answers. Even radio signals fade with the square of distance. Even lasers spread over light years. A civilization broadcasting from 1,000 light years away would, by the time their signal reached us, be whispering with less energy than a snowflake landing on your shoulder. Detecting such a signal requires not just listening, but knowing where to listen, when to listen, and what frequency to listen on. It's like trying to overhear a specific conversation in a stadium of 7 billion screaming fans, with the added difficulty that the conversation ended 1,000 years before you bought your ticket. So what would Feynman ultimately say if you cornered him at a chalkboard and asked, straight out, why hasn't an alien spaceship arrived? I think he'd laugh, that quick, sharp Feynman laugh, and tell you that the universe doesn't owe us company. It doesn't owe us answers. It doesn't even owe us aliens. It just is. A vast, ancient, mostly empty stage, governed by laws so strict that even the most advanced civilization imaginable would struggle to cross from one star to another. The silence we hear when we look up isn't a failure of the universe. It's a feature of it. It's the natural consequence of a cosmos built on the speed of light, the thermodynamics of energy, and the brevity of intelligence itself. And there's something quietly beautiful about that. Because if civilizations are rare and contact is hard, and signals fade, and ships can't come, then every moment of consciousness, every act of curiosity, every question asked into the dark becomes more precious, not less. We are the universe asking itself where everyone is. And the asking, Feynman would say, is the point. The answer may be a million years away. The asking is right here, right now, in you. So the next time you step outside on a clear night and look up at those distant, indifferent stars, don't feel small. Feel rare. Feel improbable. Feel like the brief, brilliant match that, against all the cold mathematics of the cosmos, somehow managed to strike. And ask yourself, just as Fermi did at that lunch table 76 years ago, where is everybody? Because in the asking, you join a conversation that may be the oldest and loneliest one in existence, a conversation between a universe and itself, conducted in the only language it has ever truly understood, the language of light, of distance, and of patient, beautiful, unbreakable physics.